This video is a continuation of kinetics, and it will focus on how to determine the order of reaction using a method called the method of initial rates. All right, so just to kind of activate the brain cells, let's imagine a reaction, some generic reaction that's reversible. How does the rate of the forward reaction, A going to B, how does that rate change over time? And I'm hoping you say that it decreases. If I asked you why it decreased, hopefully you would say because the concentration of A goes down over time as it gets used up, and if there's less A, it affects the rate. The rate of the reverse reaction, on the other hand, will increase with time because in the beginning there is no B, no product in the beginning, so the rate of the reverse reaction is 0 in the beginning. But as the concentration of B increases, as the product is formed over time, the reverse reaction picks up rate. So let's take a look at this graph at the bottom here, which is time on the x-axis and rate on the y-axis. And just as we described it, the rate of the forward reaction decreases over time. The rate of the reverse reaction increases over time. And at some point, the rate of the forward and reverse reaction becomes equal. That is called equilibrium. Now that's important to know that definition of equilibrium, that it is when the rate of the forward reaction equals the rate of the reverse reaction. Equilibrium has nothing to do with how much reactant and product are present. So concentration of the reactant and product have nothing to do with equilibrium. It is the rates that become equal. Now imagine when the rates are equal. Now, and this doesn't work on my iPad, unfortunately. All right, so these little ants are going back and forth at the same rate. Okay, so we're going to say this is at equilibrium. But the amount of reactant and amount of product are different. Okay, so just to kind of emphasize what I said on the last slide, equilibrium is when the rates are equal, not the amounts. All right, so there are several different types of graphs in equilibrium. There is the one here is the same one as we saw in the last PowerPoint with rate on the y-axis. And then I'm going to go ahead and show you another type. Here's another type with concentration on the y-axis. Now both of them have time on the x-axis. So concentration, what if I asked you, I gave you this graph and said, at what point is equilibrium reached? Now you haven't really learned that yet, but I'd just like you to make a guess in your head. Do you think it's reached at A, B, C, or D? It turns out that C is the correct answer, and I'm going to explain why. First of all, let's make sure you can interpret the graph. The concentration of reactant decreases, so that represents the reactant, the black curve. And concentration of product starts at 0 and increases over time. So that's how you identify what curve represents reactant and what represents product. Now, if you mistakenly said B is equilibrium, that is not correct. Okay, B is where the lines intersect. That is where the concentrations are equal, and that's a meaningless point. Okay, on the last graph, we wanted the intersection because the last graph was rates on the y-axis. Why is the correct answer C? Well, what's going on at point C? The concentrations are certainly not equal, but look what's happening to them. The concentrations are no longer changing. Okay? Concentration are no longer changing. So the concentration of reactants and products are constant at equilibrium. And so you got to pay real close attention to what's graphed on the y-axis. All right. Here's a similar graph, and this is a graph representing the decomposition of dinitrogen tetroxide gas in the atmosphere to nitrogen dioxide. And it turns out that nitrogen dioxide is the primary component of brown smog, which we see quite a bit in the summertime in highly developed cities that create a lot of pollution, like LA, for example. And it turns out that this reversible reaction, when it's at high temperature, so when the temperature is high, the forward reaction is favored. And so that's why in the summer, when the temperature's high, there's more smog overhanging. But anyway, back to the graph. At equilibrium, okay, when there's no observable change in the concentration of reactant and product, it may look like the reaction has stopped because as much as you monitor things, you can't see any change. But a reaction never stops. It turns out that, that's why we call it dynamic equilibrium. It turns out that the forward and reverse reaction keep going, again at the same rate if we're at equilibrium. Alrighty. What's the purpose of kinetics other than define the rate of reaction? Well, obviously the rate's important for monetary reasons, but just as important or more important is if we study kinetics, we can learn about what we call the reaction mechanism. And it turns out that if you have a reaction like A going to B, that it doesn't necessarily happen all in one step, A going directly to B. It might go through a series of intermediate steps, which we call elementary steps, to get to the product. And there's really no way of knowing that unless you investigate it on a more microscopic scale. So the individual pathway a reactant takes to get to product is called the reaction mechanism. And so we're going to learn a bit about that in this chapter on kinetics. We've mentioned that the rate of a reaction depends on the concentrations of the substances reactant, but it depends at different degrees on each reactant. It turns out that it's possible that a reactant may have no effect on the rate of reaction. It's possible that the concentration of a reactant may have a directly proportional effect. And it's possible that the concentration of a reactant may have an exponential effect on rate. And there's no way of knowing that unless we do experimentation. Okay, so you cannot look at a balanced reaction and predict which of the reactants is going to have what type of effect on the rate. So I told you there were a bunch of graphs in this chapter, so let's look at a few more. Instead of having time in the x-axis, notice here we have the concentration of some reactant versus rate on the y-axis. So I want to talk about different scenarios. In this particular reactant, if we increase concentration, what happens to rate? Nothing. No effect on rate whatsoever. If you hear a squeaking, that is one of my dogs chewing a squeaky toy, sorry. So we call this zero order. Okay, so that reactant has no effect on rate. Now let's check this second graph out. As we increase concentration, what happens to rate? It also increases. In fact, it's linear, so that is a direct proportional relationship between concentration and rate. When there's a direct relationship, we call it first order. That reactant is first order with respect to the rate of reaction. And to the far right, as we increase concentration, the rate increases exponentially. Okay, extra. So this particular reactant is has the most sensitive effect on the rate of the reaction. We call this second order, and you won't typically see any reactant that's above second order. Just as kind of an aside, there is something in kinetics called the collision theory, and it simply says that reactants must collide in order to react. And so keeping that in mind, when you're asked what things can increase the rate of a reaction, it becomes pretty obvious that why concentration affects rate of reaction. If reactants have to collide in order to react, if you make them more crowded, if you add more reactants, your rate's going to go up because you have more collisions. And really, anything at all that increases the rate of collisions will increase the rate of reaction. We'll talk about some of the other effects later. Alrighty, so there's something called rate law. We have talked about rate being defined as the change in concentration of some reactant or product over a certain amount of time. So that is different than the rate law. The rate law is a mathematical expression that actually gives us more information. And the generic form of it is here, where rate equals some rate constant, lowercase k, times the concentration of each reactant raised to some power, which we refer to as the order of reaction. That's just what the last slide went over. That exponent, x and y, tell you how sensitive the rate of reaction is to the concentration of that species. Now, I'm going to emphasize again that the order, these exponents, have absolutely nothing to do with the coefficients in the balanced chemical reaction. So don't make that mistake. The only way to know what the exponents are is through experimentation, lab work. That is the only way. All right, so going back to the different orders that a reactant can have, remember the generic form for the rate law, okay? It's K, rate constant, times the concentration of reactants raised to some power. All right, so now what if the reactants are zero order, okay? So let me just show you what that would be. Let's say reactant A, and it's zero order. So what is anything raised to the zero power? It equals 1, right? So this rate law then becomes simply rate equals the rate constant. That is what a zero order rate law does. Okay, first order rate law is implying that the order of reaction with respect to the reactant they're talking about is first order. Okay, and so this is the format that the rate law would take. Second order, a couple different possibilities. Second order overall could be you have two reactants and each of them are first order. What does that tell us? That tells us that to find the overall order, simply add the exponents together. And second order could also mean you only have one reactant, but that one reactant is second order. Here is some models that are representing different reactions. We have 4 of them, 4 different reactions. And the only difference in these reactions are the concentration of the reactants, the initial concentration of reactants. So for example, looking in box A, the concentration of reactant A is 3, and the concentration of reactant B is also 3. Compare that to experiment B. The concentration of blue is still 3, but what's happened to the concentration of red? Red has gone from 3 to 6, so we have doubled the red concentration, doubled the red reactant. All right, so we're starting to talk about the method of initial rates, and this is one method that is used to determine the order of reaction. That's what the exponent is for each of the reactants. So let's do one of these at a time. What is the order with respect to the red reactant? let me erase some of my scribblings here. What is the order of reaction with respect to the red reactant? So listen carefully to the procedure. When you have a situation like this where you have multiple experiments and each experiment has a different concentration of reactants, you want to pick two experiments where the concentration of one of the reactants stays the same. Okay, so blue is constant. It's not changing when we compare A to B. And then you also want the concentration of the reactant you're interested in to change. So red now is going from 3 to 6. So we have doubled the concentration of red in going from A to B. All right, so now that you've determined what two experiments to look at and how much the concentration of one of the reactants has changed, you now want to look at the effect on the rate of reaction when you have changed that concentration. So the question is, when we double red, what happens to the rate? Nothing, okay? The rate has the same amount, 1 to 1. So there is no change in rate when we double the concentration of red. What does that tell you about the order of reaction with respect to red? Well, let's go ahead and start writing the rate law, which is the purpose of these experiments. We now know one of our reactants we're going to call red, and we now know that it is 0 order with respect to the red reactant. There's no change in rate. Let's go through the same process for the blue reactant. If you think that you can do it, go ahead and shut off the video for a quick minute and see if you can determine the order with respect to blue, and then I'll discuss that for you. All right, so the first thing to do is to decide which of these 4 experiments can you compare. Now, since we're trying to find the order with respect to blue, we want the concentration of red to be constant. Okay, so how about comparing A and C? Will that work? Let's see, A has 3 red and C has 3 red. That's awesome. I want red to stay constant because I'm trying to figure out the effect of blue. Now, blue has gone from 3 in experiment A, and it's doubled. It's gone to 6 in experiment C. So the concentration of B, comparing experiment A to C, doubles. What has happened to the rate of the reaction in going from A to C? It has increased by a factor of 4. All right, so I want to carefully go over how you determine the order with respect to B, because some of these get a little bit more complicated, so there's a little bit of a math that goes with it, but I want to explain that in the next slide. So to determine order of reaction, when we did the 0 order, it was very easy, but it won't always be that easy. So remember the generic form for a rate law, and that's rate equals rate constant times concentration, in this case, red, times concentration of blue is the other reactant, and they each have some order, right? All right, so when we're doing the method of initial rates, when you have several experiments with different rates and different concentrations, what we're going to do is we're going to compare the rate for one experiment. In this case, I'm going to say it was the rate of C, experiment C, and we compared that to the rate of experiment A. I think A and C were the 2 we compared. And so I'm going to write the generic rate law for A and C. Now, they're going to have the same format. The only thing that's going to be different between these 2 rate laws is the rates, okay, and also the concentrations. So I'll just designate that. All right. So in this case, what we were just doing is determining the rate with respect to blue. And when we picked experiments A and C, we picked those because the concentration of red was constant. So rate constant K doesn't change. It's the same reaction. And the concentration of red doesn't change in these two. So this rate comparison simplifies a great deal. So it ends up being the ratio of the rates in the two experiments you're comparing equals the ratio of the concentrations in the two experiments you're comparing. Now, the trick here is that the concentrations are raised to some power y, the order, with respect to blue. So you just have to be careful. Don't forget that. All right, so what is the rate of C over A? I always like to put the larger rate on top. Otherwise, you're going to deal with fractions. I don't like that. It'll still work, but so the rate of C to A, if you go back to that data, if you need to, was 4. Okay, rate C was 4 times faster than rate A. What were the ratio of the concentrations? Well, there were 6 blue reactants in reaction C, and there were 3 in reaction A. All right, so then how do I rewrite this equation? I write too big, don't I? I'm going to simplify. I'm going to say 4 equals 6 over 3 is just 2, right? So what does y have to be in order for this equation to be correct? Y has to be 2. And that tells us that the reaction with respect to B is second order. Okay, so now that we have determined the order with respect to each of the reactants, what is the rate law? It turns out, let me just show you or remind you of what we've learned. We learned that it was 0 order with respect to red, which I guess they're calling A, right? Yeah. And it was second order with respect to blue, which I guess they're calling B. Right? We know that anything that's 0, anything raised to the 0 power is equal simply to 1. And so the rate law then simplifies to K times the concentration of B squared. That is it. So that's kind of a pictorial representation of finding the order of reaction from the method of initial rate. So now let's do an actual problem. Real quick before we get started on the problem. Again, this is a method we're using now, and that is when you run several different experiments, each using a different concentration of reactant, and then monitor the rates of each of them. We are also going to, in the next PowerPoint, learn a different way of determining the rate of reaction, and that's by making graphs and what's called the integrated rate laws, but we're not going to worry about that right now. And this is a summary slide that will help you. I don't ever recommend memorizing something without understanding it, but sometimes just getting a list of things helps the puzzle pieces. And so for any first order reactant, first order rate, the change in the rate will be the same as the change in concentrations. Okay, so if it's first order, there's going to be a direct relationship between change in rate and change in concentration. So in other words, if you double the reactant concentration, you will double the rate. If you triple the reactant concentration, you will triple the rate. Anytime they're the same, that is first order. If a reactant is second order, that means that we have a relationship like, let's say we have the concentration of A, and second order means the exponent is 2. So let's look at the possibilities here. If we double the concentration, what effect can we expect on the rate? 2 squared is 4. But I don't want you to think that's the only scenario. What happens if we, let's say, triple the concentration of that reactant? What is 3 squared? 3 squared is 9. So that means the rate, if we triple the concentration of a reactant that's second order, the rate will increase by a factor of 9. So be careful when it's second order. And of course, zero order. Any reactant that is zero order means it has no effect at all on the rate. So whatever the rate was before you change the concentration, it will remain so. Alrighty, finally, here is a typical example of the type of problem you might see. Again, this is the method of initial rates. All right, so you can see we have several different experiments. Each line represents an experiment, and each of these experiments has different concentrations of the reactants. So if you look at the overall reaction, let me write it out for you. Hydrogen peroxide decomposes, and that's the stuff that most people have in their bathroom, right? People used to clean wounds with it. I don't know if that's so much recommended anymore, but hydrogen peroxide is pretty unstable. That's why it's in that dark brown container where light can't get through, because it decomposes into water and oxygen gas pretty easily. Anyway, and iodine is the catalyst. So, but still a reactant. So let's look at, let's find the order of reaction with respect to the hydrogen peroxide and the iodine, one at a time. So look at all these experiments and tell me, now this is something you should be able to do at this point, tell me which 2 experiments I should look at to determine the order with respect of hydrogen peroxide. Now, if you think you can make it through this whole problem on your own, please give it a shot. That's much better for you than listening to me. All right, so I want to find out hydrogen peroxide. I want the iodine to stay constant while I change the hydrogen peroxide concentration. So I'm just going to compare experiment 1 and 2, okay? So you can see the iodine has remained constant. And what has happened to the concentration of hydrogen peroxide? It's increased by a factor of 2. Okay, so if 0.170 divided by 0.0850, you'll find that is a factor of 2. What has happened to the rate of the reaction? Remember, this is generic expression for rate between experiments 1 and 2. It has also increased by a factor of 2, just a pinch more, but it's experimental data. It won't be perfect. All right, so intuitively, probably a lot of you remember or can intuitively figure out that when the change in concentration equals the change in rate, that means it's first order. So if we start writing the rate law, we could write that hydrogen peroxide, we know it's first order, so we could put a 1 there, and then move on to the iodide. All right, I'm going to switch colors here. All right, so what 2 experiments should we choose to determine the order of reaction with respect to iodide? Again, all of the other reactants besides the one you're trying to figure out should be held constant. So we have to pick 2 experiments where H2O2 is held constant. So let's do 4 and 5. There are more than one choice. Okay, so if we do experiments 4 and 5, H2O2 is held constant, which is good. The concentration of iodide is increased by a factor of 2. What happens to the rate? The rate of reaction has also increased by a factor of 2. So now it turns out that both reactants in this example are first order. And so here is our rate law. It was pretty easy, right? If it's first order, you can put a 1 as an exponent if you want, or just leave it out. Either one's fine. Here's another one for you to try. This one's a little bit trickier, so if you'd like to challenge yourself, I recommend turning the video off and giving it a shot. And I will walk you through it. So let's start out by starting with nitrogen monoxide, and let's figure out the order of reaction with respect to nitrogen monoxide. I usually like to start by writing the generic expression for the rate law. Okay. And so let's look at nitrogen monoxide first. I'm going to go ahead and choose experiment 1 and 2 to compare because concentration of hydrogen gas remains constant. And what has happened to the change in concentration of nitrogen monoxide? It has doubled. What has happened to the rate of the reaction when the nitrogen monoxide concentration has doubled? Well, if you put that into your calculator, you will find that rate has increased by a factor of 4. It's not exactly 4, but you can round it as long as it's reasonably close. So you may know off the top of your head what order that is, but I'm going to go through that little bit of math in case you're ever asked to show your work or in case you get an order of reaction that is just odd. You need to be able to do this. So again, I always like to put the larger numbers in the numerator. So I am comparing experiment 2 to experiment 1. I have 2 on top just because the numbers are larger, but you could put 1 on top. And remember that I can leave out the rate constant K from these ratios, and I can also leave out the concentration expression for the reactant that's staying constant. So now I have the ratio of the rate of experiment 2 over 1 equals the ratio of the concentrations of nitrogen monoxide for experiment 2 over the ratio of the concentration of nitrogen monoxide at experiment 1. And the concentrations, again, are always raised to some power. So now plugging in the actual values, what do we get? All right, so the rate of 2 is 5 times 10 to the minus 5. The rate of 1 is 1.3 times 10 to the minus 5. Concentration of nitrogen monoxide for experiment 2 is, that's a weird format, isn't it? 0.010 molar. The concentration of nitrogen monoxide for experiment 1 is 0.005. All right, and here is my exponent. And if I go ahead and simplify the math for that, what do I get? Well, the ratio 5 divided by 1.3 is around 4, close enough. And the ratio of the two concentrations is 2. Okay, so what does x have to be in order for this mathematical equation to be correct? X must equal 2, so it is second order with respect to nitrogen monoxide. I made such a mess on the last side, I went ahead and switched to this one. So here we go. Second order with respect to that. Let's look at hydrogen gas. You want to pick again 2 experiments where the nitrogen monoxide is held constant. So that would be experiment 2 versus 3. All right, so what has happened to the concentration of hydrogen comparing 2 and 3? It's increased by a factor of 2. What has happened to the rate when we have doubled the concentration of hydrogen gas? It has also increased by a factor of 2. So what is the order with respect to hydrogen gas? Anytime the factor, the change in concentration, equals the change in rate, that means first order. So here's our overall rate law, and hopefully you can practice a few more orders of reaction, get confident with that. because once you find the rate law, you will often be asked to solve for the value of the rate constant K. So how do we do that? It's simple, but it's easy to make kind of a silly mistake. So all you do is you can use any of the experiments that are done. All you do is go back and plug in the values in the table. Okay, so you want to plug in the value for the concentration of nitrogen monoxide, plug in concentration of hydrogen gas, and plug in the rate that goes with that, and then rearrange and solve for K. So here's the math for that. The initial rate, we did all experiment 1 here. You can use any of the experiments. So here's the rate. We're plugging everything into the rate expression. Here is concentration of nitrogen monoxide. Make sure to square it because it's second order. And here's the concentration of hydrogen gas. Now, to solve for the rate constant, we have to divide both sides by these concentrations. Don't drop your exponent. I see a lot of students do that. And then plug all that into your calculator. And I would go ahead and do that now because plugging scientific notation into your calculator is a really common source of mathematical error. And so hopefully when you do that, you get 260. And now I want to talk for a minute about the units for K. Units for K are really, really important. And the units for K differ depending on the overall order of reaction. So what is the overall order of reaction for this? In order to get the overall order, you simply add together the orders of all the reactants. 2 plus 1 is 3. So this is third order overall. Okay, so it turns out that the units for K are specific for the overall order. So any third order reaction will always have these units. Any second order reaction will have a different set of units. Every first order reaction will have yet a different set of units. So we'll talk about the units. They are important. In this case, for the overall order of 3, the units are molarity to the -2, second to the -2. Another way of expressing that, these minus exponents simply mean those values are in the denominator. So I could write this as 1 over molarity squared times second. And we also know that molarity is moles over liter. So we could also write this, breaking the molarity up into moles per liter. So that, whoops, how did that happen? Let's see. All right. So that would give us liters squared over moles squared times second. And if we want to put that all in the same line, we would end up with this. All right, so that's third order overall. Let me show you mathematically. Now, of course, you can memorize these units, but it's better to understand where they come from. So, first of all, really important, the units for rate. Now, this isn't a rate law, just for rate. And remember now, what is rate? Rate overall is the change in concentration over the change in time. So the units for rate are always molarity per second or minute, whatever the unit of time is. So you see that here. So when you're solving for K, make sure you include the units for the rate and all the concentrations. And then just do the same math with the units as you did to the values. So, of course, concentration is molarity. And there's your exponent here. So let's look at all the units we have. We have rate on top. I didn't know that would cover that up. Never mind. All right. So we have rate on top, molarity per second. We have on the bottom, we have molarity squared. And we have another molarity. So together on the bottom, we have molarity cubed. Hopefully you see that. So there's 1 molarity in the numerator. There's 3 in the denominator. So we can cross one of them out in the top bottom, right? So what we have now is molarity squared in the denominator because we've canceled one of them out with the one on top. And this second is actually belongs in the denominator, right? Because it's molarity per second. So what do we have? We have 1 over molarity squared times second. That is where these units come from. So you should practice that a bit too. That is considered important in doing kinetics. So here is, to leave you with this PowerPoint, here is a summary of the different units for K depending on the overall order of reaction. Remember, if a reaction order is 0, that simply means that the rate of the reaction equals K. So what that also means is the units for K for a 0 order reaction equal the units for rate. Remember, units for rate is always molarity per second. Alrighty. If you have a first order reaction, so rate equals K times concentration of something raised to the first power, it turns out that the units are 1 over seconds, which can be expressed like this. And we can quickly, I'm not going to show it to you for all, but I'm going to show it one more time for this. So if we were solving for K from an order of 1 over all, to rearrange this, we would say K equals rate over concentration of A raised to the first power. Then carrying our units along, rate is always molarity over second. Concentration is molarity, and there's only an exponent of 1. The molarities cancel, and so for an overall first order, you're simply left with 1 over time. That's where that comes from. Okay, second order overall and third order, which is what we just did on the last slide. So I want you to take a minute and I want you to look at the units going from 0 order all the way to third order. And I want you to see if you see a pattern. This is just helping you remember, like if you're stressed out in a test. Do you see a pattern in what's happening to the units starting here and moving our way down? I'm going to put these in terms of molarity. I think it's easier to see. So 0 order is molarity over second. First order is 1 over second. Second order is 1 over molarity times second. And third order is 1 over molarity squared times second. I think that's easier to see a pattern. What's going on here? What's the pattern? Do you notice that in going from a lower order to a higher order, each time we divide by molarity? So if you have 0 order, you divide by molarity, you get 1 over seconds. Divide by molarity again, divide by molarity again. That just might help you remember it. That is it for this PowerPoint.